All right, here we're going to look at graphing log functions. A log function, the easiest way to think about it is that it is the inverse of an exponential function. So everything I know about an exponential function, I'm going to reverse it. Because remember, an inverse means it's the opposite. I'm going to switch the x and the y. So that's what this definition up here is telling me. That if I have a log function, I can really switch it to become an exponential and vice versa. Okay, that's if and only if means I can go both directions. So now that I know already from our last section what an exponential function is, all I need to do is do the inverse operation of everything. So let's remember about an exponential function. An exponential function had a domain which was negative infinity to infinity, and a range of 0 to infinity. So remember, domain is my x's, range is my y's. So if I were to switch those, now the log function, the domain is going to be 0 to infinity. And our range is now going to become what the domain was, which is going to be negative infinity to infinity. So they are just literally switching spots. All right. In an exponential function, we had a horizontal asymptote, which was a y. So now we're going to have a vertical asymptote, which is an x. So again, I'm just switching the x with the y. Our table of values that we were graphing with used to be negative 1, 1 over a. I'm going to switch that and make it 1 over a, comma, negative 1. Used to be 0, 1, now is 1, 0. Used to be 1a is now a1. So everything is going to be the opposite when I look at an inverse function. So my log function comes directly from doing the inverse operation of my exponential. So the first thing that we want to do is just see if we can rewrite an equation that's written as an exponential into a log and vice versa, from a log into an exponential. So remembering that these functions are inverses of each other, I want to see if I can rewrite them, meaning that I'm going to switch the x's and the y's, and the base of the log is going to become the base of the exponent, and vice versa. The base of the exponent will become the base of the log. So the first one we're going to look at is changing an exponential into a log. So what that means is the base of the exponential is going to become the base of the log. So it's now going to be log a. And I'm going to switch the x and the y, which means 24 will be with the log and 4 will be on the other side of the equals. All right, let's look at the next one. I'm now going to write the log of w, switch, so it'd be z equals k. All right, last one here, I would say log e 17 equals 5. Now, let's talk about this last one here. There's actually two types of logarithmic functions. There's a log function and there's a natural log function, essentially doing the same thing, but the difference is that if I have e as a base, I actually want to use natural log instead. All right. Now, either way is going to work, but just so we can kind of get an idea. All right. So this time we want to go from a log function to an exponential function. So with a log function, I'm going to take the base of the log is now going to become the base of the exponential. And I'm going to switch, so 5 will be the exponent and 7 will be the other side of the equals. All right, let's look at the same thing here. We've got 9 is our base. 8 is going to become the exponent, and k is on the other side of the equals. All right, b is going to be our base. G is going to be the exponent, and W is going to be on the other side of the equals. So all we want to do first is just be able to change them back and forth from a log to an exponent to a log, knowing that they are inverses. All right, so the whole idea of actually looking at this idea of log and exponential being inverses of each other is to be able to graph a log by knowing what an exponential looks like, okay? So when we look at just the basic log function, when we had a exponential function, we actually had two kind of base functions. We had, or parent functions, we had a exponential growth and an exponential decay. However, with a log function, we just want to look at one basic function, which is our log base function, okay? So when we look at just the general log function, thinking about what we did in the very beginning of this video, switching the domain and the range, the horizontal to the vertical asymptote, switching the table that we were graphing from, we come up with this parent function of a log here. The properties being that the domain is 0 to infinity. The range is negative infinity to infinity. It will have a vertical asymptote at x equals 0. The ordered pairs will come from the table 1 over a, negative 1, 1, 0, and a, 1. All right? Now, I can't graph this unless I actually know what the base is of the function. Just like an exponential function, I couldn't graph it until I knew what the base was, so I knew that it was growth or decay or that kind of thing. Okay? So let's say that we want to graph our parent function of a base 2, a log with a base 2. All right, so the domain is going to be 0 to infinity. The range will be negative infinity to infinity. The vertical asymptote will be x equals 0, so none of that changes. The only thing this base helps me do is be able to come up with a table of values. So I'm going to have 1 over my a, so 1/2, comma, negative 1, 1, 0, and then a, so 2, comma, 1. So I graph those 3 points, remembering that as I approach an asymptote, I'm going to approach infinity or negative infinity. So in this case, as we approach our vertical asymptote, we're going to approach negative infinity. And then off to the right, it's going to go to positive infinity. Okay, so that's what the most basic parent function of a log will look like. Now, just like with an exponential function, we wanted to transform it. We want to do the same thing with a log function. We want to transform this function from the parent function, moving it up, down, right, left, stretch, shrink, reflect, all that good stuff. So what that means for our function is that we want to determine what are these transformations going to do to the most basic elements, the domain, the range, the vertical asymptote, the points. Okay, so that's what we're going to look at. Now, in an exponential function, remember the k, or our up-down motion, was kind of the big transforming unit here. But in a log, the big transforming unit is actually going to be our h. If you think about that, it's because the x is now important, whereas in the exponential function, the y was the more important one. Okay, so now I'm going to look at this h value, how I'm moving right and left to determine what this vertical asymptote is going to be. It's also going to determine what my domain is going to be. The range in a log function is now going to be all real numbers, similar to what the domain was in an exponential. Okay? Remember, the way we were getting our table of values was we were going to get our original values and then transform them by whatever the transformations say. So we'll generate a new table. So let's see what that looks like graphically. Okay, so looking at this first example here, I'm just going to describe it first so we can kind of see what's going on. I see a I see a minus 1 here. So that means that we're going to move to the right 1. I see a plus 2 here, so I'm going to move up 2. 3 is going to be the base of our function, which is our a. And now what we want to do is we want to be able to generate the vertical asymptote, the domain, the range, and be able to graph it just by knowing these things. So let's see what we've got here. All right. So because I'm moving to the right one, remember the x is the selling factor here for my log. Because I'm moving to the right one, I'm now going to have a vertical asymptote at 1, which means that my domain is going to be from 1 to infinity. Remember, my range is always all real numbers, so that's not a big deal on this one. The main thing is remembering which one is which, like which properties go for exponential and which properties go for log. Okay? So in a log, my range is all real numbers. My table is going to start with 1 over that a, negative 1, 1, 0, a, which is 3, 1. All right. Now that's my original points, but I haven't transformed them yet. So let's transform them. If I move to the right 1, I'm going to add 1 to all of my x's. If I move up 2, I'm going to add 2 to all of my y's. So let's go ahead and transform our function and see what new points I'm actually going to go graph. So adding 1 to all of my x's will give me 4/3, 2, and 4. Adding 2 to all my y's will give me 1, 2, and 3. So really, my ordered pairs that I'm going to go graph are going to be 4/3, 1, 2, 2, and 4, 3. Okay. Remember, I also need to graph that vertical asymptote. So I'm going to start with that. Vertical asymptote there at x equals 1. I'm going to graph my point 4/3, 1, 2, 2, and 4, 3. As I connect the dots here, one side is going to go vertically approaching that asymptote, and the other side is going to go off to infinity. All right? Let's look at our next function here. All right? Again, I'm going to start by describing it. Here I'm going to see this 2 is going to be a stretch by 2, which remember when we looked at exponential, we said a stretch is really going to look like how far away or how close to the asymptote I actually am. So a stretch means I'll be a little bit further away from the asymptote versus a shrink means I'll be actually closer to the asymptote. Okay? So I'm going to see a stretch of 2. My base or my a is 4. I'm going to be moving to the left 1, and I'm going to be moving down 3. All right? So let's see what that does for my elements. I'm going to have a vertical asymptote here at x equals -1 because I was moving to the left. Okay? Which means that my domain is going to be -1 to infinity. My range, remember, is always all real numbers for this function. Okay? My original table before any transformations is going to be 1 over 4, comma, -1. Remember, it's 1 over a, and then -1. 1, 0. A, which is 4, and 1. Okay? Now, remember, that's pre-transformation. So let's transform it now. I'm going to move to the left 1, which means I'm going to subtract 1 from my x's. I'm going to move down 3, so -3. I'm going to stretch by 2, so I'm going to multiply by 2 on those y's. Okay, so let's transform and see what happens. Subtract 1 from all my x's, which will give me a -3/4, 0, and 3. Multiply by 2 and then a subtract of 3 for each of these y values is going to leave me with -5, -3, and -1. All right. So then what that means is my ordered pairs are going to end up being -3/4, comma -5, 0, -3, and 3, -1. Right, so I go graph my vertical asymptote here at -1. Okay, graph my ordered pair -3/4, -5, 0, -3, and 3, -1. And I'm going to approach the asymptote, and I'm going to approach infinity. So I can see, if I compare those two graphs, I can see that the points are a little bit more spread out in the second graph because of that stretch of 2. I'm not going to see it really, really big because I'm only stretching it by 2. If that had been like a 5 out in front, I would really see huge jumps between my 3 points. Okay. Now, one thing to remember, I kind of talked about this whenever we were looking earlier at our log function, but log in general has 2 basic forms. A log with no base is known as a log base 10. The easiest way that I remember that is that the log literally looks like a 10G. So the way I remember that log without a base, so if they put no number here, I know that that's really a log with a base 10. They will not ever put a 10 there. I just have to know it. Okay, kind of like a square root. They don't put a little 2 there, but I just know that it is a square root. Okay, so just like that, I know that a log with no base has an implied base of 10. Okay, we talked about a natural log earlier. A natural log has that implied base of an e. Remember e being the number 2.71, similar to pi, right? We had that whole discussion earlier. Same idea here. So a natural log, which is called an ln, okay, is going to have a natural base of the number e. So when I see natural log, it won't have anything there, but I know that it's got an e as a base. Okay, so knowing that, I just want to try 2 more just to make sure that we've got it where we don't have these bases. Okay, so the first one I want to look at is our natural log. So we're going to describe it, do everything exactly the same. I start off, I see that I'm going to have a stretch of 3. I'm going to have a base, or an a, equaling to e, which is at 2.71. And I'm going to be moving to the right 2. Okay, so once I know that, I'm going to come up with my vertical asymptote, which is going to be, because I'm moving to the right, it's going to be x equals 2. My domain is going to be 2 to infinity. My range is going to be all real numbers, or -infinity to infinity. All right, so let's get our table going here. I start off with 1 over my a, -1. 1, 0, a, 1. Remembering that e is really 2.71. So what that'll honestly look like, 1 over 2.71 is 0.37, and e is 2.71. Okay, so just as we go to transform these, we'll have a better idea of what's going on. So I'm going to transform these functions. Since I'm moving to the right 2, I'm going to add 2 to my x's. Since I'm stretching by 3, I'm going to multiply my y's by 3. All right, so let's go ahead and do that and see what values that we get. So adding 2 to my x's is going to give me 2.37, 3, and 4.71. Multiplying by 3 on my y's is going to give me -3, 0, and 3. So my ordered pairs will end up being 2.37, -3, 3, 0, and 4.71, 3. All right, so I've got my vertical asymptote here at 2. And then I've got my 0.2.37, negative 3. I've got the 0.30 and the 0.4713. Again, I'm going to approach the asymptote and then go off to infinity. Okay? So really, having a natural log versus a log only changes just the table, and it's just the numbers will be decimals. That's really it. Okay? Let's look at this last one where we have our log with its common base of 10. Right? So the first thing I'm going to do is I see that I have no base, so I know that my base, or my a, is going to be 10 here because it's log. I have a plus 5, so I'm going to be moving to the left 5. And then I have a minus 3, so I'm going to be moving down 3. Okay, so let's see what that does to my elements. I've got a vertical asymptote here is going to be at x equals negative 5 because I'm moving left 5. I've got my domain, which is going to be from negative 5 to infinity. I've got my range is going to be all real numbers. Okay. My table before any transformations is going to be 1 over 10, negative 1, 1, 0, 10, 1. All right. Now I'm going to transform those by going to the left 5, so I'll subtract 5. And going down 3, so I'm going to subtract 3 from those y's. So let's do that and see what happens. So I'm going to end up with a negative 4.9. I'm going to end up with a negative 4, and I'm going to end up with a with a positive 5. Sorry about that. All right, on my y's, I'm going to subtract 3 each time. So I'm going to end up with a negative 4. A negative 3, and a negative 2. So my ordered pairs that I'm going to graph are going to be negative 4.9, comma, negative 4. Negative 4, comma, negative 3. And 5, comma, negative 2. All right, so let's get our vertical asymptote going here at negative 5. All right, then I'm going to have my first ordered pair, negative 4.9, negative 4. Really close to that asymptote. Negative 4, negative 3. And 5, negative 2. All right, I'm going to approach the asymptote, and then I'm going to go off to infinity. So now we know how to graph a logarithmic function, also a natural logarithmic function, and their transformations.